Good afternoon, everybody. My name is Ben Follett. I am the U.S. Product and Marketing Manager at SCIA in the United States. Today, I appreciate you giving us the time. Today we're going to talk about seismic analysis of building structures and specifically how that relates to our software, SCIA Engineer. For those of you who are maybe new to the GoToWebinar setup, you have some audio controls. If you're having issues with your audio, please use the sound check to make sure your speakers are working. If you have any questions, you can enter them in the questions field. Dave, our sales engineer, and myself will be available to answer questions during the meeting, and then also we'll have a Q&A session after the meeting. And then once the meeting ends, we'll actually post the recording to YouTube, and then you'll also be sent a link to download that recording. So a little agenda for today. Today we really want to focus on seismic analysis. So we'll talk about the different calculation approaches of eigenfrequencies on the structure. We'll talk about analysis using equivalent lateral force procedure, which is very widely used here in the United States. We'll talk a little bit about the modal response spectrum analysis. One of the most important things about seismic analysis and a requirement of code is the obtaining of 90% mass participation. So we'll talk about a few different ways that SCIA handles that. We'll also then talk about accidental eccentricity, results per story, and also results for seismic loads, and then finally seismic combinations. So let's go ahead and jump right in. So in SCIA Engineer, we have to do a few things to first to calculate eigenfrequencies in the software. The first is the creation of mass groups. Mass groups can be automatically generated using the load cases, the linear load cases that are already created. We can also manually input masses, either as point masses, line masses, surface masses. We then need to create a mass group, just like a combination would be created. And so these are the masses that are associated with all permanent gravity loads and then any variable loads that you want to include into this system as well. And so these get combined based on just kind of your simple equation of combining all permanent loads and then the variable loads with typically a factor, maybe a 0.3 factor on the live loads. And so let's just go ahead and jump in to see how this actually looks in SCIA Engineer. And so this is SCIA Engineer. I just have a basic project here. In the project settings of the software, we have functionality already pre-established. And so in this case, I already have dynamics enabled and the seismicity enabled for those dynamics. When I want to set up a dynamics project, I first need to look in the dynamics tree window here. And the first thing I need to do is I need to go ahead and actually establish masses. And in order to do this, I could either create masses on my own or I'm going to create mass groups. So in this case, we get mass groups created automatically for us for self-weight. I can also create a mass group for dead load, so one that's bound to the load case of any dead load I have already in the linear load cases, and then I can also create one for our live load. Okay. Now with this information, we can go ahead and create all the masses and then generate all the masses on the structure. So here it's just generating different masses based on the line loads and the surface loads and the point loads and other things that are already created in the model. Now, once I have all the masses created, I can go ahead into the combination of mass groups, and like we talked about, I can go ahead and add all the masses in and then just create a simple combination. So in this case, I'm going to add a 0.3 factor to that mass group 3, which is the live load mass. Now, a few settings for the dynamic analysis. I can establish them in the solver setup, so I can choose the eigenvalue solver that we want to use. We have a few different. I'm going to choose this first one here. We can then just set the number of eigen modes in this case, and so maybe we'll choose to set 16. And then we can go ahead and run the analysis. So I'm going to go ahead then and run a batch analysis that will include the linear and modal analysis. And so while this is working here for a second, SCIA can run other types of modal analysis, not just a seismic modal analysis in this case, or not just a modal analysis based on the mass of the structure. We can also just do a simple free vibration analysis. We'll see a little bit later that we'll define some more seismic loads, and we'll go ahead and add a seismic response spectrum and use that information in the model. So now with our results available, we can go ahead and look at results for, say, we can go ahead and look at results for deformed structure. We can go look at other different variable results on our model, and then we can go ahead and take further steps to look at other results like story forces and other seismic related results. And we'll go ahead and look at those in a little bit more detail later in our presentation. So one of the newest things that's been added to the software is the calculation or the analysis for equivalent lateral forces. So this method, obviously a static analysis method where the seismic action is distributed based on a base shear and then based on the height of the structure per either the provisions of the Eurocode or the provisions of the ASCE. Here we just have some simple requirements for whether you're doing this in the ASCE or you're doing this in the Eurocode. Obviously, we're very familiar with these, or most of us are very familiar with these. And so in SCIA, obviously, we're calculating that base shear based on the weight or based on the mass that we apply to the structure. In SCIA, we have three calculation methods that are possible, basically how we can calculate the period or how we want the load to be calculated. So we can either choose a maximum acceleration of this overall spectrum. We can choose to allow the software to calculate the fundamental period automatically for us based on the provisions of the ASCE, or we can choose a selected eigen mode, and after looking at maybe the deformed shape or looking at where the mass participation is in a specific mode, we can go ahead and look at the information and then apply or pick where we want to calculate those forces from. We're also distributing the horizontal seismic forces either in a linear method, a method that's proportional to the mode shape, or obviously in a polynomial method, which is straight out of the ASCE code. Now we also have what we call the reduced analysis model, and we'll take a little bit more time later talking very specifically about what the reduced analysis model is, but it is a model type that's essential for using the equivalent lateral force procedure, and when we talk about that a little bit more later, we'll see why that's important. And so again, I'm going to go ahead and jump back into SCIA Engineer. I'm going to actually switch models here. So one thing you'll notice is it's possible to have multiple models open in SCIA. I have 4 or 5 open in this juncture. And so I've got a model here, the same kind of structure. I've already run some analysis on it. The first thing I want to do is I'm going to go into the libraries and loads, and I want to look at this seismic spectrum. So I created a seismic spectrum based on the IBC code here, and we can see all these provisions where we can define the site class, the R value, the seismic risk category, and then the importance factor and the seismic design category are automatically calculated for us. We then input the SS, the S1, and the long period, and then the rest of the information is calculated for us. Now this information then, if I go ahead and cancel out of this, this information then is used to establish our seismic load cases. And so if I open load cases here, we can see both the EX and the EY load cases that have been created. So I'm applying this seismic spectrum, this DC quake in this case, and I can have more than one seismic spectrum if I wanted to do test different things or look at different cases. I then can go ahead and set how I want to do equivalent lateral forces, because like we'll see a little bit later when we talk about modal analysis or a modal response spectrum analysis, we don't have to do equivalent lateral forces. It's not required. And so in this case, I'm choosing the polynomial distribution, and then I'm choosing to calculate the fundamental period based on the provisions of the ASCE. So here we see those. We choose those provisions, so I'm just choosing the structure type and then whether or not we want to calculate the height from the model or we want to calculate that ourselves. Then we can also include accidental eccentricity. Now we'll talk about, again, more about accidental eccentricity later. And that's set up for both the direction for the EX and the EY directions. Now when we go ahead and look at results, again, we have all different types of results that are available to us. The result that's probably most important and most synonymous with information with equivalent lateral force is a summary result for story forces. And so here we got a story data, this force total on the story for this seismic load EX. So if I go ahead and refresh this here, we can go ahead and look at a preview, and apologize, it popped up on my other screen here. We go ahead and look at a preview then of the information of how the forces are calculated. So the values for acceleration, the distribution factor, the fundamental period which was calculated, and then the information by floor of the mass, the height of that floor, and then the total force at each level. Now we can see I had set that we have basically that this one level is below grade, and so obviously it's not taking into account any force, and we can set the level of where we want the force to kind of terminate at. So we can set kind of that basement or ground level so that even though there might be mass below the structure, that mass isn't getting taken into account in the generation of force and overall base shears. Okay, now like I mentioned, obviously the equivalent lateral force procedure is probably most widely used here in the United States, but we also have the ability, or in many cases, there's times when you just can't use the equivalent lateral force procedure anymore. And so you need to jump into that kind of Chapter 12, Section 9 of ASCE and jump into a modal response spectrum analysis. And so obviously this is applied to the types of buildings which don't satisfy the conditions of ELF, whether it's a non-regularity in elevation, whether it's a height restriction, whether we're past a certain site class or seismic design category. And really in this case, this is a response to really the vibration of given eigenmodes and how they contribute to the global response of the system. And so the one thing that we know in the code, the one thing that we've all kind of seen is we need to effectively kind of take into account modal masses in all the modes that are greater than or equal to 90% of the total mass of the structure. So that's one of the biggest, or that is the biggest, in order to have kind of a useful or usable seismic analysis, is to have that 90% mass participation. And then all modes within the effectual modal masses greater than 5% are taken into account, right? That's another kind of requirement of this system. And so really what we end up finding out is, or we end up kind of discovering, is that this may in some cases be very difficult. And so really how do we, how can we, or what can we do in software, what can we do within SCIA to allow for an easier achievement of that 90% mass participation ratio? And so the first thing is that we offer different methods for taking the mass or the modal mass into account. The first is what we call participating mass only. So it takes into account only the calculated modes masses. So essentially when we saw the options in the solver setup a little bit earlier, we saw that there were, I selected the number of masses, so, or excuse me, the number of eigenmodes, so it was going to be one eigenmode, or 32 eigenmodes, or 16 eigenmodes. So it's only then going to take into account that the masses that are in those modes. We could also include what we call missing masses in modes. Basically, this increases the results obtained from the calculated modes. So essentially, if we've obtained a modal mass of 80%, or if we have a modal mass that's 80% of the total mass, we can amplify those results by what we would assume to be the missing mass in those modes. The other is we can include what we call the residual modes. This is the missing masses that are associated with other rigid parts of the structure that are maybe not vibrant in this case. These masses are subject to maybe ground accelerations, and so we can actually include those residual masses as a residual mode, as kind of a secondary mode in addition to what we've already applied, such that we can include them and try to better obtain that 90% mass participation. And so here's just kind of a little example. This was the same kind of just wall or the same kind of project. Just a quick comparison. This is when 80% of the total mass was mobilized, kind of what we have going on. And so, you know, we've got the participating mass, the missing mass, obviously, which is going to kind of create a lot more, and then that residual modes. And so that we see that the results of 90% of the total mass mobilized was about 85.5 kips. And so we can see that both the participating mass and the residual mode gives us a pretty good result for getting pretty close to that 90% mass participation, whereas the missing mass in modes really increases it probably above and beyond where we'd like to go. Now another way that we in the software help to kind of get to this 90% mass participation ratio is what we call the reduced analysis model. So the reduced analysis model, or we call it the IRS, is really a model that was created, or an analysis and model type that was created in order to help us achieve a better, a more accurate 90% mass participation criteria when it comes to most models for dynamic analysis. And so what this kind of aims to solve is typically we have local modes in a structure. So this is that same structure that we were looking at. We have these local modes that are just a vibrating or kind of sinusoidal curve on a set of beams or a couple different beams. And what this does is that it creates additional eigenmodes, which then really don't have an impact on the larger structure. And so we really want to filter these out. We really don't want to take these into account because they really just create for us the need to create more and more and more modes, right? We can add more modes. You know, we could create 64, 128 different modes, but really that's just going to up the calculation time. It's going to up the amount of information that we have to kind of sort through and sift through, and it's really not that useful. You know, we have these global modes, right? These are very kind of plain to see when you're looking at deformations and deflections on the structure. You know, we see that we have these global modes of the structure, you know, all kind of moving in one direction, or all kind of twisting in one direction, or all kind of heaving or something in one direction. And so in this case, this is where the majority then of the mass is activated in a particular mode. Maybe not the majority, but a large portion of the mass is activated in a particular mode. And so in that case, you know, we know that this is going to be kind of a useful a mode then, and that's going to really contribute to that 90% mass participation. Now, you know, one of the other things in this case too is also, you know, one of the things that's done kind of historically in finite element analysis, or when trying to do finite element analysis and include dynamics, is the fact that many people replace slabs. So on the left here we can see that I've got a model with 3-foot finite element mesh, and we're meshing the slabs. So those 7 slabs, we're all meshing them. They replace slabs with diaphragms. And so those diaphragms tend to you know, make the model a little smaller. They make the model a little bit more manageable. They allow for maybe a simpler transfer of loads, but then they also reduce the fact that you're not viewing the results on a finite element mesh in the in the fullness of the finite element mesh on all the stories, and then maybe you have to have a secondary model for slab design and so on and so forth. And so this reduced analysis model is really at its core is a matrix condensation technique that reduces the number of degrees of freedom of the structure relative to the original mesh. And so it has what I think are the following advantages. So you don't have to create diaphragms, because if you can see in this little picture here, we have kind of the full 3D model with floors, and what it does during the dynamic analysis in the modal analysis is it reduces this system really down to this system where all the mass is kind of clumped at individual story levels, and this is why it's really useful for the equivalent lateral force procedure, because we have that requirement that we have to integrate or have forces and mass at specific story levels. And so then that allows us to also eliminate local modes. So since we're kind of lumping masses at levels, any of those kind of local modes, which tend to happen based on small localized masses and their kind of vibration, they're now lumped at a level, and so now you have more global mass working together. You also have better convergence of this modal mass. Obviously we get to 90%, a little bit higher, and we drastically reduce the computation time. And so, and the last thing is that it's not just, we're not now limited in the results that we can view. So this reduced model kind of runs in the solver in the background, and then we're able to actually retrieve the full mesh results after running the solver through this model type. So in this case, we only have 2 specific requirements for using this in the software. The first is you just have to define stories. And so typically when you're doing a building-based structure anyways, you have stories, and so as long as stories are defined, you can very easily do this. The second then is just a checkbox for activating the IRS model within the solver setup, and we'll see that. We're going to go ahead and look at a few different examples of different types of models and how we use the IRS method in just a little bit. Now just some kind of stats. You know, this is the same model that I was using. We have a comparison of basically this effective modal mass as resulting from the 32 calculated modes. So in the standard model, you can kind of see here that we have modes 1, 2, and 3 have a decent amount of mass that are kind of engaged, if you will, in these directions. So in the x direction, y direction, you know, you've got a decent amount of mass. Also in mode 10, you've got a decent amount of mass. But all summed over the 32 modes, we have about 70% of the mass kind of engaged in both the x and y directions. Now, when we use the reduced IRS model, that reduced model, the same 32 modes, we've got 92%. And so we can see in some cases we can actually reduce the number of modes because we're going to achieve, we're going to achieve a much higher mass participation just over the first 4 modes here, and not having to maybe need 32 modes, and then overall we're going to achieve the mass participation that we need in order to really effectively and accurately do a seismic analysis. Now another option that we can do is just some modeling options using what we call property modifiers. So property modifiers in the system allow SCIA to modify the self-weight of certain elements. So in cases where you think you're going to have local modes and you're going to have local vibrations, we can actually reduce the self-weight to 0, or not even necessarily reduce the self-weight, but even just reduce the mass. And so we have the option to do either of those. We also can modify the stiffness. So in this case, for concrete models, if you want to include information about with cracked elements, we can reduce the stiffness. In this case, you can see it in this kind of stiffness factors 2D section here. Reduce the stiffness by the axial stiffness by 50%, or so on and so forth, so that we can actually create a more accurate system, and so that load can kind of get into the places where we need it to, so that it vibrates and gives us mass participation that we want. We can also, again, modify the mass. So in this case, we can manage immobile masses. So maybe the whole bottom of the structure is supported by something that we don't want to take into account. It's got mass, but it's not really going to vibrate. It's not really going to move in any direction during the modal analysis. So we can take that mass and lower it down to 0, such that basically now these immobile masses aren't really taken into account. They're not really affecting the overall design of maybe the structure above. Maybe in this case it's like the mass of the parking garage that's below grade, not having to be taken into account for the remainder of the analysis of the pedestal building or the building that's above the parking garage, right? So this really allows us, in that case, not only to get more accurate results, but now maybe you don't have to build 2 separate models, right? So you don't have to kind of create more work for yourself because you're trying to get the seismic analysis to work the way you want. The last kind of tip or trick in obtaining 90% mass participation ratio in SCIA is with sign results and sign displacements. And so modal superposition implies a loss of associated forces and signs. So the signing of these results allows us to find those kind of appropriate resulting forces. So essentially what we have here is, we get an intensity of the force from the spectral analysis, right? So we have this force kind of intensity. This is kind of just a little frame or something here. But we have kind of the intensity in the force. The results of the predominant eigenmode then typically define the sign, right? And so this is the predominant eigenmode. This is, definitely part of the information is, part of this intensity is maybe coming from this predominant eigenmode, but it's defining then the sign of the system. And so in that case, kind of combining these, if you will, we get this system. And so what this ends up giving us is when we have unsigned results, right? We have results that are just kind of, from a seismic event that's moving in one direction. We may have just the results, and there's there's nothing. They're all just forces. In this case, maybe all positive forces. But in this case, when we have the sign results, we see kind of that flip, that kind of tension compression, if you will, on the system. Where you see that okay, truly have the tension, truly have the compression or the shears here, such that we see how the system is really reacting. And so this allows us, this is a step towards closer to actually getting us that 90% mass participation. And so we get better forces, and this is included within the eigenmode solver of the software, and so we can get better signed results and get us better overall results for for the seismic load cases. Now, displacements under seismic action should also be calculated on the basis of this elastic deformation of the structure. And so in SCIA, typically there's a couple different things that you can do with this, right? So you have the option to just not amplify the displacements. So if no amplification is required, then the results are sufficient, and we can utilize those results in the design of the system and the checks for story drifts and so on and so forth. You can also do a manual amplification right now of the displacements using the CD over I factor, and we can just create that in a load case or in a load combination. So really what a lot of people are doing, and typically what a lot of people are doing regardless, are creating specific load cases for the strength level system for seismic and then the serviceability system for seismic, and then being able to take that information and then apply those to different combinations such that they now can check their strength and serviceability requirements different. And so maybe in this case it's not even creating different seismic load cases, but it's then just creating different seismic load combinations, using the seismic load combinations, which we'll talk about a little later, from ASCE to do the strength level design, and then using other seismic load combinations with maybe the inclusion of the manual amplification to get data for serviceability so that you can check the serviceability of the structure. Okay. So we also, I mentioned earlier that I wanted to talk a little bit about accidental eccentricity. And so there are two types of eccentricity that can be taken into account inside the SCIA model. The first is obviously is structural eccentricity, and this is just automatic in the 3D model, right? You've got eccentricities that are built into how the structure itself is modeled and created, and because of that, you're going to get eccentricities that exist. You know, if you take an element and you offset it or you apply an eccentricity to it just from its analysis line to its line of load application, you know, you're going to generate structural eccentricities. The second is accidental eccentricity. Obviously, this is eccentricity of the mass or the application of static loadings consisting of a set of torsional moments about the vertical axis of each story. And so this is dead out of those two codes as well. And so the software then takes those story forces and then calculates those torsional moments based on that story force, and then based on its center of mass or center of rigidity in that case, gets that value of E, that eccentricity value, and then can calculate that, that torsional moment. And so the story forces then obviously are derived from the distribution of accelerations on the height of the structure, right? So we can have a very simple linear distribution on the structure. We can have, and this is kind of very similar to what we have in the equivalent lateral force procedure, right? We've got kind of a linear or even a polynomial distribution. We can actually get a calculation of these based on a distribution of accelerations from a specific eigen shape or strictly from modal superposition. And so those are all options within when doing a modal analysis, or like we saw earlier, when doing a equivalent lateral force procedure analysis, we can select our method for calculating these story forces in the given model. So let's go ahead. We've gone over a lot of we've covered a lot of topics, but I want to actually jump back into the software here, and I want to look at a few different models to just kind of show you, kind of live and in living color, some of the data that we talked about. So the first thing I'm going to do is I'm going to switch here to this model, and I want to use it to talk about you know, one of the things that we brought up in how to better achieve 90% mass participation, which is by using property modifiers. And so I have some property modifiers already established. I'm going to go ahead and actually enable these property modifiers. So we'll go ahead and enable these property modifiers. So I'm going to go to labels, and we'll turn on, let's see, we'll turn on labels of other model data here, and we'll turn on our attributes, okay. And then we'll turn on one other thing here, and labels of other model data, okay. So now if I go ahead and select for instance, a wall, we can see in the properties here that we have a property modifier assigned here. And so we can go ahead and select this property modifier. In this case, you know, we're using the 50% stiffness modifier. So I have a couple different for a diaphragm or for 50% stiffness or 100% stiffness. And then we can see here we've got a self-weight factor and a mass factor. So we could reduce the mass factor, we could reduce the self-weight factor. If we look down maybe at one of these walls here and look at the property modifier, we can see that the mass factor of this wall, this is a wall that it's a basement wall that I've chosen is below the line of kind of analysis line that we want to start with our equivalent lateral or our seismic load calculation. We've reduced the mass. So it's immobile mass that we don't want taken into account. Now in this case, I ran not an we didn't run an IRS method, so that improved reduced system method. We just ran a straight modal procedure, And so if we go ahead into our results and we look at the calculation protocol, we can get a really quick view of, maybe we need to rerun this here. There we go, it's down at the bottom here. We can get a really quick view of the information in this calculation protocol. And so we look at the table sum of masses and then the table factors. We can see we have, in this particular model, we've got, we have something that's maybe a bit lower than the mass participation. So we've got 70, 60% mass participation in this particular model. So we haven't used the IRS method. We didn't kind of lump those masses together. We just allowed all the masses to kind of vibrate as they would without having to take in any additional care of it. So we have a 70% mass participation. This is what we talked about a little bit earlier. And so now if we switch to, I'm going to switch to another model, same model, but now what we've done here in this case is, we've gone ahead and we've enabled that IRS method. So in the solver setup here, we have this improve reduce system enabled. So remember, we talked about the only things required to use this improve reduce system is to enable the checkbox and then also have stories set up. So now with these, with the checkbox enabled and the stories set up, we can go ahead into our results and again into calculation protocol, and we can look at the table of output here, and now the table of factors, the same 32, we've got now 92% mass participation in both those X and Y modes here. And so that really allows us to get to the place where we need to be a little bit more quickly, a little bit more efficiently, so that we don't have to spend the time really, messing around and trying to immobilize mass or trying to eliminate local modes. And so now, the final part of this that we talked about is what do we do about accidental eccentricity? So if we go into the load cases here, so I have a few different load cases established, the EX and the EY. Now in this case, I didn't use equivalent lateral forces. I just used the IRS method with modal response spectrum analysis. But we can now also enable accidental eccentricity, right? So we can go ahead and choose how we want to enable the accidental eccentricity. So linear distribution of accelerations. In this case, we apply kind of that eccentricity, that 5% eccentricity there, in that case. And then you can see here that when we use an accidental eccentricity, it actually creates for us a separate accidental eccentricity load case. And so this accidental eccentricity load case can be viewed separately, so in the analysis we can look at the results of that separately, or we can actually look at the results of that. It'll actually create for us kind of a grouping of the seismic load and then the accidental eccentricity together, so that we kind of get an overall picture of the load and the output for that particular case. And so that's what we get when we create this accidental eccentricity within the load case. And so it is going to create a separate load case for us, but it's not a load case that we're creating on our own. We're creating it right from the seismic load case here. So let's go ahead and switch. I'm going to look at my last model here. So again, the same model, I just have some results run for, in this case, the accidental eccentricity. And so if I go ahead into the results, I'm going to go into our story and our summary results. And we can look at some different results for, say, EX. And we can look at results for, story, different results for story data. And so if we open this up here, let's get the table results open. We can go ahead and see, we can look at story result data for like mass, for center of the center of mass, or the center of or the location of the center of mass, and then total mass on the structure. So let's go ahead and we can look at different displacement results. So these are, these are story displacements, right? So we're looking at story displacements at each level per a certain load case. We can also go ahead and see, so these are displacements in inner story drifts. We can also go ahead and look at detailed results. So if we go ahead and look at a detailed result, I'm going to select then you can see here for this combination, which is seismic load EX with accidental eccentricity. I'm going to go ahead and look at internal forces on the model. So we're going to look at internal forces on a model. And I want to look at the axial forces on a specific selection. So I'm going to look at the name selection here. and we'll go ahead and run this name selection. So let's go ahead and get this. I'm going to go ahead and look at a side view here so we can get these floors. So let's look at the table results here. Okay. So let's look at single story here. So let's just take a second to generate. We're going to generate all these forces then on this particular story. And so we can look at, these are those signed results that we were talking about. Let's go ahead and look at the 5th floor. Here we go. We can look at all these different signed results so that we can see the different results that are kind of shown here. Here we go, in this particular floor. And so let's go ahead and look. I'm going to isolate this floor so we can see only this floor. And let's go ahead and get a transparent view of the model. So here's transparent. And let's go ahead and rerun this. And of course now it's not showing the way I want it to show. Let's get everything back here. Oh, there we go. Wrong floor. So we can see those forces. So we've got these forces on the columns, we've got these forces on the walls and at different locations. And these are those internal forces. And so we're either looking at internal forces or we can actually set resulting forces, right? So we want to find out what the total, moment, at a floor is. We can go ahead and look at the total moment and the total, the total axial or the total force at a particular moment for a particular cases, and its, and its location about that center of mass or center of rigidity. And so we can look at all this information and use all this information to our advantage when trying to do our seismic analysis. Now we mentioned a little bit resultant forces, so whether it's resultant per story like we were looking at or base shear, we can go ahead and either get a base shear by doing resultants of reactions, and so we could take all our reactions and get accurate base shear. We could also be a little bit more specific, and we can actually apply a section to say around, for instance, a core wall or a set of shear walls, and get a force and an overturning moment for that entire kind of assembly of shear walls. That's possible as well. Obviously, for the equivalent lateral force procedure method, we're getting resultant by stories, or we can actually only specify specific story results or floor elements to get to see how those elements or the mass within those elements accounts for results load-wise in that particular story. So we don't even have to take into account the entire story if we don't want to. So we can really kind of fine-tune the results and things that we're looking at. All different types of resultant forces obviously are available in this detailed results. So we can look at wall and column forces like we were looking at before. Like we saw, we can choose a level or a section that we want. We can get a total load, or we can average based on element. We can get the internal forces, or we can get the kind of the group forces for the entire floor or the entire grouping of elements. We can also, it gives us results that aren't just seismic results. This is available for static results as well, linear analysis results as well, so we can include both of those. And then obviously this also gives us information for like load distribution, so it gives us a good idea of when you have a rigid diaphragm or a semi-rigid diaphragm and you are applying lateral load, how is that lateral load being taken into account, and how's it being, how's it being taken by certain moment frames or certain concrete moment frames or certain shear wall elements or shear wall cores, and how do openings in the slab really change that. And so really that gives us a good idea or a good way to look at the shear distribution or the load distribution through essentially a diaphragm in this case. Now the last thing I wanted to mention, this is actually a new improvement for version 16.1, which is out in the next week or so for the American code, is automated or automatic seismic combinations created per ASC 710. And so just some of the following features. You have the ability to include both your X and Y direction seismic loads in the same load combination, like I have here created in this contents of combinations. You can include the vertical distribution, or you can choose a checkbox to not include the vertical distribution. It's really up to you. You have the ability to include redundancy and overstrength. So we're including either a redundancy factor of 1.3. When you include overstrength, you can actually and decide whether or not you want to include the overstrength combinations with the standard combinations for seismicity, or if you want to create a very, a separate set of load combinations, a separate envelope of load combinations for overstrength. I know that's something that people typically want to do since they're using the overstrength combinations to do a different type of analysis. They're typically using them like on connections or in other seismic regions, doing different things. You can also automatically create the orthogonal combinations, so the EX plus, for instance, the EX plus 0.3 EY, and so that can automatically be included just by choosing some of the settings in the load cases, whether or not they are going to get applied together. And so when they're automatically applied together, they're automatically applied in a way that's 100% and then 30%. And then obviously we can include accidental eccentricity in any combination. So when you create a combination and you apply seismic load, that accidental eccentricity gets included in there, or can be included in there as another part of the seismic load. And since that accidental eccentricity only appears as a function of the original seismic load, so in this case, this accidental eccentricity only is created as a part of this seismic load, it's automatically going to follow that load. So it's not going to get applied in its own or on its own in its own case or anything. So it'll get properly applied to the system, so you have proper loading. So just kind of a quick summary. We have really two main ways, and really the code even prescribes, for the most part, two main ways to do seismic analysis, whether it's the equivalent lateral force procedure or the modal response spectrum analysis. So those have a set of common settings in the software, whether it's the generation and combination of masses, you create eigenfrequencies, you generate or create a response spectrum, and you create seismic load cases. Those are all the same. And then where we deviate is obviously the choice of using equivalent lateral force or selecting to do modal response spectrum analysis. You must activate that IRS method, that mass condensation technique for equivalent lateral force, and that's really because you want masses lumped at levels. And then you can choose what you want to do about the fundamental period in the equivalent lateral force, whether you want to input it, whether you want the software to calculate it, whether you want to do it based on a mode, so on and so forth. And then again, you've got final common settings, whether it's enabling accidental eccentricity available in both, creating and using seismic combinations in both, and then obviously running the analysis to use, the modal analysis to use and obtain those seismic results. And all the seismic results are the same. You can look at story forces and base shears and all the information for both. It's just a matter of how you set up those specific settings for either that get you there. Just a few housekeeping things. This equivalent lateral force procedure is a new module. It's included in our fundamentals, professional, and expert editions. So that's kind of our mid-range and editions. And then the modal response spectrum analysis information is included in the professional and some of the other editions as well. Right now it's actually included in fundamentals as well, and so you'll have all that functionality in the fundamentals edition, which is the edition that's really geared towards building engineers here in the United States. I guess at this time, I saw a couple questions come in. I'd like to open up this time so that we could answer some questions. And so if you have any other questions, go ahead and type them now into the chat or the questions section window, and then we're going to go ahead and answer as much of them as we can. So we'll just kind of jump right into it. Somebody asked a long time ago, and I apologize for just getting to the question now, can the software be integrated with exporting a Tekla model? So yes, we do have a direct link with Tekla. It's a direct link based on mapping files, and so we can directly send a SCIA file to a Tekla file and vice versa, send a Tekla file to a SCIA file, just based on a link that we have with all different versions of Tekla. And so it's updated every release, and so we do have a link with Tekla. We don't do connection design in the U.S. right now. We can calculate the stiffness of particular connections, but not the actual limit state check. We do, however, are exploring Nemencheck, who is the holding company that owns SCIA, along with other softwares, recently purchased Design Data, who owns SDS2. And so we're in really deep discussions about integrating SDS2 into SCIA Engineer, so to better give really, they have first-in-class, best-in-class connection design, and so we really want to integrate their really advanced features, their really advanced functionality for connection design into the software. Somebody just asked a housekeeping question about the recording. Yes, As long as you're in attendance, the recording will be available. It'll be sent to you, I think, tomorrow. Otherwise, you can go onto YouTube and you can go to SCIA, search SCIA on YouTube, and it'll be posted there in the next day or so. Somebody asked which frequency is considered the final result in order to check the resonance given the load's frequency. So the frequency is dependent on the mode, right? And so you have different modes of the structure, 16 different modes, and so it really depends on you get a mass participation in the mode, so you get a period in a frequency and mass that is vibrated, that's actively participating in a particular mode, and so you would have to check the frequency based on the mass participation. So typically in that case, for a very regular building, you would have a lot of mass that's engaged in one mode in the x direction, a lot of mass that's engaged in another mode in the y direction, and subsequently you would have frequencies and periods that are associated with both of those types. So someone just had a comment about the wall stiffnesses at 50%. It was just an example, not necessarily Bible in the sense that we're not doing anything, that's not the way that we would suggest to do it. You can actually create any type of stiffness modifier you can. I know that there's some stuff in the code that's 70% and 35% for walls and beams respectively, and so you can create any type of reduced modifier that you want just by choosing to reduce the axial or bending stiffness, and so you can set up a whole host of them to say, hey, here's 50%, 60%, 70, 35, whatever, and then you can just choose from that drop-down list. I can send out a copy of the slides if you'd like a copy of the slides. I certainly don't think everybody would want them, but if you want a copy of the slides, my email address is listed right here at the bottom. Just send me an email and I can send you the most recent version of the slides for your review. There also is a demo version available. If you go to www.SCIA, which is SCIA.net, right at the top of that landing page, which is our main home page, you'll find a button for free tryout, and you just have to fill out your your information and your email address, and we can process the request in that way. So somebody wants some more information about the IRS method. I do have some more detailed documentation, so I can send some more detailed documentation. Again, if you specifically want some more detailed documentation, you can either visit our website and the SCIA Resource Center, which has some white papers written about it, or if you email me directly at my email address there below, I can send out some more detailed documentation about the improved reduced system and how it works and what it does in its mass condensation techniques in the solver. So someone asked a question about the calculation of masonry buildings. So you can do, it doesn't matter, you can create a masonry material in the software, basically just a reduction of the properties for a concrete building, and you could do an analysis in that way, so that really wouldn't change the loads that are created and applied. Obviously you could select the R value that corresponds with a masonry shear wall system or a masonry bearing wall system, and get the calculation that way. Let's see, what else do we have here? Yeah, so someone asked the question, actually user Nick, glad you were able to join us, asked a question about the R value. So the R value in the seismic response spectrum is a new. If you've been using SCIA in the past for seismic stuff, that R factor is new. So that R factor will replace that 1 over R kind of acceleration factor that's currently in the load cases. So you won't need to do that anymore. You'll just create the seismic response spectrum and use the R factor that's appropriate for your particular case there. Cable elements in seismic analysis, and that also leads to another question someone asked about nonlinear and seismic together. So the problem with nonlinear and seismic together is, modal analysis is essentially a linear analysis type, in the sense of how it takes into account the elements of the building, and so on the whole, you cannot right now do a nonlinear modal analysis or a nonlinear dynamic analysis in SCIA. However, there are ways to do things in the FEM model that allow you to allow you to create the create like axial force only members or initial stress members like cables would be, so that those can be incorporated into the dynamic analysis of the software. Yes, the building does a center. This building does a center of rigidity for the entire building and each level as well. So those would both be calculated, and those results are available to you. You can look at each floor, and then it would show you the XYZ coordinate for the center rigidity of the building, and then the XYZ coordinate for the center rigidity of the entire of each individual level. Let's see, anything else? Someone asked about Revit, which is the same thing kind of as our information with Tekla. We do have a direct link with Revit, so we have a direct link with Revit to send information back and forth between Revit and SCIA. We also use the IFC file format, so we can directly link both Revit and Tekla together with SCIA using that IFC file format. So someone asks, how can I use sequential analysis in the mass combination for to consider a nonlinear support effect in the structure in the seismic calculation? So you can do a sequential analysis, but again, even when you do nonlinear, even when you're doing a nonlinear support, which is possible in CEngineer, I'm not sure that I don't believe that nonlinear support is available during the modal calculation. I think that you would find that you would have to kind of do them separately in taking into account the nonlinear supports and then doing the modal analysis. So there was a question about, it seems that there was a question about diaphragms. Let's see here. So in SCIA, right now in SCIA, we don't use diaphragms, and that's part of the reason why we have that IRS method, is that we advocate you don't create diaphragms. You actually just allow the structure to be the structure, and then you can generate the forces, those equivalent lateral forces, or like we saw in those resultant views, the kind of the forces as they get to certain shear walls and moment frames and stuff like that. You can just, the floor system will act as a diaphragm. Now we are doing some development now to have very simplified diaphragms added into the software, and those will obviously be able to be used with the linear and nonlinear and seismic type of analysis. But right now you just use the same slabs, and you allow for them to be meshed and go from there. Let's see. Yeah, someone made mention about regular, irregular structure. That's just based on ASCE. So, I mean, you'd have to use the ASCE to determine if your structure is regular, irregular, and then determine if whether or not you can use the ELF procedure. SCIA is not going to say your building is regular or your building is irregular, therefore you cannot use the ELF procedure. You have to make that engineering decision and engineering choice yourself. Yes, there is graphical representation of different modes of vibration. I've not ever run into a maximum limit of modes. I've done models with 128 modes before, so there doesn't seem to be, I've not encountered a limit, and so you can get all different results, accelerations, displacements, forces, and everything, and show them graphically and actually show all that other information for each individual mode. So let's see. I don't see. I don't think that there seems to be any other questions. Obviously, if we didn't answer your question, we can certainly get to it. Or if you have specific questions that we didn't answer, and again, you want to email me. Directly. That's fine. Again, my email address b.follett@scia.net. And one last question just popped up. Actually, the modes can be animated, yes. So you can you can animate those modes. And so I'll leave the questions section open here for just a minute, but I'm going to end the webinar, and I appreciate the time that everybody's given. If you have any questions, please follow up with us directly, and we'll plan to follow up with just about everybody. You'll be receiving, if you attended, you'll be receiving a certificate of attendance that you can use to self-report PDHs, and then otherwise the webinar recording will be sent tomorrow, and then will also be published on our YouTube site probably in the next day or so. So again, thank you for your attendance, thank you for your participation, and I look forward to working with anybody who's interested in SCIA. Thank you very much.